Hola, mi clase. All right, we're doing 5.1 absolute value functions. So I can write, that's not supposed to be recursive and explicit formula. No, this should say I can graph. That's not what that says. I can graph and interpret absolute value functions. Just made up my own. There we go. Okay. So an absolute value function is, remember this is our function notation, f of x. So the function at x is the absolute value of x. Okay. We have to remember that absolute value means the distance that is away from 0. Distance is always measured in positives. Okay, so how far away it is from 0 is what absolute value is. Okay, we got to remember that. So, excuse me, just plugged my phone in. We have this thing called axis of symmetry. It's the intersects the vertex. We'll get to what a vertex is. I probably should have said that first. And divides the graph into two sections that are images of each other under reflection. So an axis of symmetry is a line I draw, and one side is identical and equal to the other side. Okay? And it goes through what we call the vertex. And so if we look at the last one, it says the vertex on each graph where the axis of symmetry intersects the graph. It represents the minimum or the maximum value of the range. So it's kind of like that point that makes my graph stop at, in a sense. And we'll talk about it when I show you the graphs, and we'll label the vertex. And then I'll show you where the axis of symmetry as well, okay? But it just means that if I cut my graph in half, the left side is going to perfectly look like the right side. All right, so this is our absolute value function. It's just the absolute value of x. So we want to plug in some points. So maybe I'll do -4, -2, 0, 2, and then 4, okay? So what we do is the function at x is the absolute value, so I'm going to go the absolute value of -4. And I'm going to scoot that back over. I kind of smushed that over there. I'm going to go this way. -4. Well, the absolute value, -4, is 4 away from 0, so the answer is 4. So our function, our point would be -4, 4. Okay? We plug in -2, absolute value. Try to make these lines as straight as possible so they don't look like parentheses. So -2 is 2 away from 0, so the absolute value of -2 is 2. And so we have the point -2, 2. All right, absolute value of 0. Well, 0 is 0 away from 0, so our point is 0, 0. And then absolute value of 2. Well, 2 is also 2 away from 0, so it's actually also 2. It's not the opposite. So we get the point 2, 2. And the absolute value of 4. 4 is 4 units away from 0, so the point is 4, 4. So now we're going to graph these. So -4, all right, 1, 2, 3, 4. So -4 is up at 4. -2 is at 2. 0, 0, 2, 2, and 4, 4. And then we're going to draw, and these are actually going to be nice, perfect straight lines. All right, like this. They are identical, perfectly straight lines. And that's because absolute value functions are always the same distance from each side. Oh, sorry, I was trying to move that arrow. Okay, there's no curve in this because they're moving exactly the same, all right? So this point right here is our vertex. It's where it splits the graph in half. It's my very bottom of my grid, okay? We would then have an axis of symmetry actually right here because it perfectly splits my graph like butterfly wings. So in this case, the axis of symmetry is our y-axis. It's because this side is perfectly identical to this side. So our domain is, remember, domain is all of our x's. So our x's actually just continue in both ways. So we would say what we call all real or all real numbers because it is everything. There's no restrictions on it. However, our range, which is our y, is it has to be from 0 and up. Notice I have no negatives in here. So we would say that y has to be greater than or equal to 0. Because I don't go into the negatives. All right, so that is the absolute value function. It's always going to be a perfect v as well. So then we can start doing things to it, which in this case, we're going to take the absolute value and times it by 2. So let's do -2, -1, 0, 1, 2 this time. So what it would look like is I would go 2 and then times it by the absolute value of -2. Well, the absolute value of -2 was 2. So we're going to take 2 times 2, which would get me 4. So now our point would be -2, 4. And then times the absolute value of -1 times 2. Well, the absolute value of -1 is 1, and 1 times 2 is 2. So we get -1, not 2. -1, 2. So 2 absolute value of 0. Well, the absolute value of 0 is 0 times 2 would be 0. Now, if we remember, absolute values are going to be perfect v's. Oh, see, I need to make that a straight line. So the absolute value of 1 is 1 times 2 is 2. So notice we're always going to get this very similar doubling happening a lot of the time because of that v'ing that absolute values do. All right, absolute value 2 is 2 times 2 would be 4. Oh, sorry, 2, 4. All right, so let's graph them. -2, 4, -1, 2, 0, 0, 1, 2, and then 2, 4. Again, it's going to be a nice perfect V. And then I want you to notice when I times it by 2, notice my V gets a lot steeper. It's very similar to when we times a line by 2, right? Or a slope of 2, 5. It gets very, very, very steep. All right, here's my axis. And then again, here's my vertex. It's the minimum of my graph. All right, the domain again will be all real because the x's just get to go forever and ever and ever. And then again, this time the y will also still be greater than or equal to 0 because that's as low as my y can go. All right, let's do -4, -2, 0, 2, and 4 again on this one. So this time we're going to multiply by a -1. So the absolute value of -4 is 4, but times it by -1, I actually get -4. So now we have the point -4, -4. Why don't you see if you can fill in the rest of this table? I'll fill it in, and then I want you to see if you can get these points. Okay? So maybe pause or fill in the table with me first, then pause and see if you can get these points correct. All right, so for -2, we should have gotten times 2, and then -1 would have been -2. This still stays 0. This is also -2, and then this should have also been -4. So we should have -2, -2, 0, 0, 2, -2, and 4, -4. So if I go -4, I come down here now to -4, 2, -2. Oh, I went too far, hold on. 2, -2, 0, 0, 2, -2, and then 4, -4. Again, it's going to be a perfect V. Oh, let me get the correct one I want. It's going to be a nice perfect V for us. Now, this maximum is our vertex. It's still the vertex because remember it's a minimum or a maximum. It's the highest it could possibly go this time. This is still our axis of symmetry. It's where it splits it in half. It's still our y-axis. Okay. Symmetry. So the domain is still all real because notice the x's just go on forever in both directions. This time, however, our y is going to be less than or equal to 0 because all of the y's are now negative. So we need our y's to be less than or equal to 0. Okay? And they get to be equal to, and there's no dash lines because these aren't inequality versions. Okay, you guys see that? So that's why we get to make them all solid. Oop, sorry. All right, so now we're going to talk about story problems. So Jay rides in a boat from his home to his friend's home in a neighboring state. You can see it says Utah-Arizona border right here. The graph of the function distance over time, the only reason I know that is because they're right here, equals 30 absolute value t minus 1.5 absolute value. Shows the distance of the boat in miles from the state line at t hours, assuming the graph shows his entire trip. So this is his trip. Okay, this is how long he travels, and then this is his trip. It says how far does Jay travel to visit his friend? So this is his entire trip. When he starts, he is 45 miles away from the border. So you can see this is him driving to the border. And he then drives towards the border. That's why his distance is 0. This is compared to the border, if you notice, the distance to the border. Okay, so he's driving towards the border. That's what this is. Then, once he gets to the border, he drives his boat away from the border to his friend's house. Okay, this right here is what we would call our axis of symmetry because it's where it splits it. Okay, and here is our vertex. This is the border, this dashed line right here. Okay, that's what this represents. So if we want to know how far he traveled, we have to start here. He's go by 5s. So he's at 45 miles here. He comes all the way to the border, and then he goes all the way out. And if you notice, it's actually in the same spot. So if he's at 45 miles here, and he goes back out from the border to another 45 miles, then his total trip is 90 miles. Okay, so what I did is I just looked at how far he was when he started, followed my path, and noticed where it ended. It ended at 45 miles as well. And so I just added them together because that's his whole trip. It says assume the graph shows his entire trip. And so then I just added these two distances up. So it says, what is the rate of change over the interval of 2 hours to 2.5 hours? Well, here's 2 hours, and then here's 2.5 hours. So what we're doing is we're looking for the rate of change, his speed, right here in between these two. So we just need to find the slope in between these 2 points. So we can use the graph. I can go 5, 10, 15. And then these are by halvesies. So I know that this is a half an hour, right? A half. So if I do 15 over a half, it's really 15 divided by a half like this, right? So it's 15 over 1 times 2 over 1. It's actually 30. So his rate is 30 miles per hour. Okay, because I have to clean this fraction up. Okay, so he travels 30 miles an hour, especially in this section, but we do know that this axis of symmetry means it's equal to this side. So in that same section, he's traveled 30 miles an hour. All right, so Sandy takes a hike on a 6-mile trail. She hikes from the beginning of the trail to the end and then turns around and follows the trail back. The graph shows her distance from the start of the trail after X hours. How far does Sandy travel on her hike, and how long is her hike? So all I'm going to do is just tell you that this is the vertex. and your axis of symmetry is right here. Okay, so that's all I'm going to tell you. I actually want you guys to try to complete this based off of our last example. Okay, it's very similar. The only added is how long her hike is. That's a little different. So this is kind of, think of this as your independent practice. I want you to answer these two questions. How far did Sandy travel on her hike, and how long is her hike? All right, one more story problem. I don't know if this was supposed to say Kara, but it says Kata, whatever that is. Gets on a moving walkway at an airport. You know those flat escalators? Then 8 seconds after she gets on, she taps Lisa, who is standing along the walkway. Okay, so right here is where Lisa is, but she's standing kind of next to it, right? The graph shows Kata's distance from Lisa over time. So this is where she starts on the walkway, she travels, taps Lisa, and then travels. It says calculate the rate of change of her distance for Lisa from 6 seconds to 8 seconds, and then from 8 seconds to 12 seconds. It says what does the rate of change mean in terms of Kata's movement? So we're looking for 6 seconds to 8 seconds, and then 8 seconds to 12 seconds. Okay? So if I do 6 seconds to 8 seconds, these are going by 4s. So this is -4 over 2. So from 6 seconds to 8 seconds, I have -4 over 2, which is -2. So it's -2 feet per second. Now, for 8 to 12, it's a little hard to tell. Sorry, I was just thinking. Because it's not at a perfect spot. Because sorry, I was just looking. This actually isn't at a very nice spot, so I'm gonna delete this spot. We're gonna find this slope again. I don't really like this spot. I just realized that that's not my answer, so I want to make sure I give you guys the correct answer. So we're gonna do this again. I need my eraser to be bigger. Okay, so looking at my graph closer, my graph's better on my book, and this is not at a nice spot. It's actually slightly above that point. So we're gonna use the y-intercept, her starting point, okay, which is at a nice spot. And the reason I can do this is because if you notice, this is a straight line, and so it's a constant. So if I come down, I go down negative. See, it's going to give me the same answer. Oh, no, it's not. I lied. These go by 4s. This is at 20, right? So I'm going to go down 20 over 8 this time, okay? And that reduces to -5 over 2, which is the same as -2.5. Sorry about that, feet per second. Now, this is my vertex, where Lisa is. This is my vertex. And we also know that the axis of symmetry splits this perfectly in half, that one side is equal to the other side. Okay, this is my axis of symmetry. Now, just like we did on the left side, on the right side, I'm going to want to find a point that works nicely, or it's not going to work, right? I'm not going to be able to find this slope if it's not at a perfect spot. However, I also know that this is an axis of symmetry, which means one side is equal to the other side. Okay, it means that they're moving that, I can lay that on top of the other side. Does that make sense? So if one side's -2.5 and it's going down, then the interval from 8 seconds to 12 seconds is actually the same rate, but positive 2.5 feet per second. Okay, because you can see it's a positive line. Okay, so these are the same rate because it's my axis of symmetry splits them. This is the same as this, just in the opposite direction. So 6 seconds to 8 seconds was negative 2.5 feet. 8 seconds to 12 seconds is 2.5 feet because they have an axis of symmetry. This is the same as this, okay? Now it says, what do these rates of change mean in terms of kata's movement? So what I want you to do is just answer that last question. What does that mean? Why is this one negative? What does that mean in order for her movement? And again, remember, we're kind of comparing it to Lisa's spot here, and then that this side is positive. Okay, so I just want you to answer this last question. All right. So things to remember: axis of symmetry splits the graph perfectly in half. That's the main thing I want you to remember for today, okay? And then absolute values always make a V. How about that? Absolute value functions make a V shape. All right, you can hear that lunch is over. That's right, I gave up my lunch for you guys. All right, adios until next time.